In a previous video, I showed you how I built a metal lathe from industrial scrap. Now, I have added a vertical mill to this lathe, also using materials from the local industrial scrapyard. We'll first remove the tailstock and the tool holder. The mill frame is made from 80mm aluminium profiles, with 2 braces for extra rigidity. A backplate is added, which can be fixed with 4 screws. The backplate has 4 rollers that fit in the profiles. The backplate can be moved left and right via a lead screw. The mill uses a Morris chuck, which I got from eBay. It can hold up to 16mm bits. The mill spindle is held in taper roller bearings that sit in a housing and can be preloaded via a nut. The spindle is directly driven by a 50-volt 500-watt brushed DC servo motor via a flexible coupling. 2 15mm linear guides are mounted on the backplate, and the complete motor assembly rides on these guide rails. The bottom spindle mounting plate can be fine adjusted via 4 long bolts. The motor assembly can be moved up and down via a lead screw with a worm gear drive coupling that gives around 1mm vertical movement for 1 rotation of the handle. Via a stop, the motor assembly can be set at a fixed vertical position. The vertical readout is done via a digital caliper. The motor speed is controlled by a home-built speed controller with tacho feedback. The unit is powered via a 50-volt 800-watt power supply. The lathe carriage and cross-slide now serve as the mill XY table. The cross-slide caliper is moved to the left side and a 20mm thick metal plate is bolted onto the cross-slide. As mill vise, I used separate metal blocks that can be bolted at different positions onto the table. The moving jaw can be moved via a 20mm bolt. The movement is slightly more than the distance of the holes in the plate, so any size object can be clamped down. The mill chuck centerline matches with the lathe chuck centerline, which is handy for drilling holes and milling slots in parts that are clamped in the lathe chuck. For this purpose, I mounted a divider disc with 48 holes onto the lathe spindle. The backplate assembly can move 25 cm horizontally and the motor assembly can move 35 cm vertically. The XY table can move 25 cm in X direction and 20 cm in Y direction, which is quite okay for such a small unit. The total weight is now around 100 kilograms. I can still slide it to the side of my workbench when not in use. The aluminium profiles were cut to size and fixed with bolts to the lathe motor housing and rear plate. The 90-degree brackets and T-nuts make it easy to slide and adjust the horizontal beams. The braces were made from 8mm aluminium and fit nicely into the profile slots. They were tapped and bolted to the profiles at the top and bolted to the rear plate and motor housing at the bottom. The construction is now sturdy and stiff. Here you see the assembly of the chuck, spindle, taper roller bearings and bearing housing, which came from an old pick-and-place machine. The motor housing was made from 12mm and 8mm aluminium. I used my router to mill the sides of the plates. Here I'm cutting the hole for the bearing assembly. I'm using the holes of the bearing housing as a guide to drill the holes in the plate. The motor housing is almost finished. We can now mount the spindle, add the spacer and tighten the nuts for setting the bearing preload. The flexible coupling can be fixed as well. The guide rails are slid into the blocks. Here you can see the vertical stop with the T-nut that will grip the backplate. The backplate is also made from 8mm aluminium. It can be fixed to the profiles with bolts and T-nuts. Here I'm drilling and tapping the holes for the guide rails. I used my router and the guide rails to mill a slot in the backplate for the vertical stop. The backplate and the guide rails need to be perfectly square to the lathe bed. Here I'm turning the aluminium rollers for the backplate. I'm turning all four together, making good use of my home-built lathe. The end result looks quite nice. The bearings fit well in the rollers, which are then bolted to the rear plate. The roller height can be adjusted to fit the profile slot. Now the motor assembly can be bolted down and the stop can be mounted. The lead screw assembly that moves the motor assembly also came from the scrapyard. The bronze nut is bolted to the side of the motor housing and the lead screw drive box and top end bearing are fixed to the rear plate. The lead screw that moves the backplate is made from M12 threaded rod. I had to turn down one end to fit the bearings and tap an M8 thread at the rod end. Here is the end result. Now I'm turning the bearing housing. And drilling the holes for the bearing housing mounting. I made this jig for drilling straight holes in the profiles. Which works quite well. After mounting one side of the bearing housing, I assembled the lead screw assembly to have all components in line. Then I add some cyano glue to the bearing housing and the profiles. Now I can drill the holes and tap the thread. And assemble everything again. Then we can place back the backplate assembly onto the aluminium frame. A square nut can be positioned and the holes can be drilled. The nut is then bolted to the rear plate and the assembly can be moved via the lead screw. The power supplies I used also came from the scrapyard. I think they came from old telecom equipment. They have a 12 volt and an isolated 48 volt 7.8 amp output. I placed two units in parallel to get around 800 watts of power. These supplies are designed for forced cooling, so I added two fans. The holes in the housing use some mesh cloth to keep debris out. The end result is a nice compact housing that fits at the top of the mill. Here you can see the speed controller circuit, which you can also download from our website. The two power supplies are paralleled via balancing resistors. The power stage is similar to my lathe speed control, with tacho feedback and an OLED display. I also added motor current sense, which is then shown as torque on the display. I used isolation routing method for making the PCB. Draw the component location and copper traces by hand on 0.1 inch grid paper. Then punch the holes for the leaded components. And drill the holes. Then I cover the top side with marker pen ink as a background for the carbon paper that I use to transfer the topside copper layout to the PCB. Then I use an engraver tool with a fine dental milling bit to cut away the copper to form the copper islands. This process is then repeated for the bottom side. Finally, we need to make sure there are no shorts. Some top layer holes need to be isolated from top layer copper. In this design, the two power components are mounted on the housing bottom plate for cooling. Now we can solder the SMD components on the top side and the bottom side. Then come the leaded components. Finally, the power components are soldered in place. After some programming, we got a working speed controller. Before final assembly, everything has to be aligned well. Here I'm making sure that the aluminium frame is parallel to the lathe bed. After placing the backplate assembly, I'm adjusting the rollers to make sure that the motor mount rails are square to the lathe bed as well. Then the roller bolts can be tightened. And checking everything is square again. If all is well, the mill chuck and the lathe chuck center lines are perfectly aligned. Now the power supply can be mounted and the speed controller can be mounted. All the wires need to be connected. Including the tacho feedback cable and the speed control front panel. When all is wired, we can switch on the main switch, dial in the required milling speed and flip the switch. Let's test the torque reading. I set a lower RPM and try to slow down the chuck with my hand. You can see that the speed stays constant, but the torque reading increases due to the higher motor current. For the mill vertical movement indication, I'm using another digital caliper, which is mounted to an aluminium block with a slot in it. A bracket is mounted to the side of the motor housing, and the caliper block is slid over the bracket. The other side is fixed to the motor housing. The vertical movement can now be accurately checked and zeroed at any position. Now it's time to mount the mill table. First, 9 holes are drilled in the cross-slide plate. The readings from the calipers make it possible to drill the holes very accurately. Then drill the mill table center hole. Then I use the cross-slide plate holes as a guide to drill the mill table holes, which will get well-aligned holes. Now we can start milling the sides of the mill table. This is the first use of the mill and seems to work well with light cuts. For facing the mill table surface, I built a kind of fly cutter. First, I fixed my lathe spindle with the dividing disc. Now I can mill a slot in the metal round stock that will hold an SCMT carbide insert. The slot milling looks good. Now we can turn the shaft on the fly cutter. Here is the final result. I decided to mount 2 inserts for balancing the tool. First, I did a trial on a piece of scrap to see how the fly cutter works. The surface finish looks nice, but there are clear steps in the 2 adjacent passes. This is caused by the milling head not being fully square to the lathe bed surface. I checked this with a dial indicator on a glass plate. The milling head plate can be fine adjusted with the 4 long bolts. It took some effort to get the mill head well adjusted. But now the indicator shows it's perfectly square in all directions. The mill head bolts can now be tightened. Let's try a few surface passes again. There are no more steps between the passes. So now we can mill the surface of the milling table. The end result is a perfectly flat table surface. I originally planned to mill T-slots in the table, but a few trials showed that it takes a lot of time. This 15mm T-slot milling took around 1 hour. Therefore, I decided to drill holes each 14mm and the rows of holes 60mm apart. The holes method will also keep the table more rigid compared to a table with T-slots. The XY table makes drilling holes very accurate, and the mill motor torque is sufficient to drill aggressively. The vertical caliper ensures each hole is 13mm deep. Now we can tap the M8 thread in each hole, first using the mill chuck to start the thread straight, then finishing the tap by hand. For the mill vise, I found a bar of tool steel on the scrapyard that was nice and square at all sides. I cut it with an abrasive disc. Before I could mill this, I needed something to clamp it to the mill table. So I made these simple low-profile clamps from scrap metal. First, cutting the slots with an 8mm mill. The result is not too bad. Then milling the front surface. Now the stress relief holes need to be drilled. Then the sides can be cut off and the vertical slots can be cut. Some top milling is needed, which gives me some more practice. Then the holes for the clamping adjustment bolts can be drilled and tapped. Here you see the final parts. First, we mount the low-profile fixed jaw to the table and make sure it is parallel with an indicator. Now the part can be clamped to the table using the other movable jaw. After tightening the bolts, the part is well clamped. Now we can start milling the roughly cut surface of the vise fixed jaw. And after drilling the holes, the recessed slot for the bolt heads can be milled with a 13mm mill. Now the final vise jaw can be bolted to the table and adjust it to make it parallel. And we can finish the other vise pieces. Here I'm drilling the holes for the rods, which need to be very accurate through all pieces. I finally use a 12 mm reamer through all parts. Then some more slot milling and tapping the M12 thread. Now the parts can be assembled. As you can see, the rods fit well and the assembly slides perfectly straight and flat on the mill table. It would have been very difficult to make this with my simple drill press. Let's use the vise to clamp a 60 mm aluminium block. After positioning and bolting down the movable jaw assembly, the movable jaw can be pressed against the block with the M12 bolt. The block is securely clamped. Now let's clamp the block using high parallels. After tightening the vise jaw, one of the parallels comes loose. This is because the movable jaw tends to lift when the block is clamped at the top of the jaw. To overcome this, I can use the two bolts to clamp the movable jaw to the table surface. Now the block sits well on the parallels again. Let's make a 28 mm cube from this 30 mm square aluminium bar. First I cut 30 mm length with my circle saw. I'm using a milling method that I learned from Joe Pasinski's YouTube channel. First we need to make the block square. The mill depth is around 0.7 mm. This milling direction and sequence gives almost no burr. Now we can make a light pass around all the edges. Then the other side of the block can be milled using the same milling direction and sequence. As the top and bottom surfaces are now parallel, we can clamp them directly in the vise. One of the milled sides sits on a single low parallel. We can now mill the four sides using the same sequence. After all four sides have been done, the block is now square. We still need to mill it down to final size. We can now use two parallels to hold it. I need to take around 0.61 mm off one side. So I set the mill on the surface, zero the caliper, and then set the milling depth to 0.55 mm to make sure I won't overshoot the 28 mm final size. After milling this surface, let's check the dimension again. Almost there. I increase the milling depth another 0.03 of a millimeter and do another pass. We should now be to final size, so I can mill the other surfaces as well with the same milling depth. The final dimension is pretty close to target, not too bad for a first trial. One of the things I learned from this build is that rigidity for a mill is even more important than it is for a lathe. This lightweight construction is of course nowhere near as rigid as these heavy cast iron machines, but for soft materials and light cuts, this mill seems to do quite okay. It takes about 5 minutes to convert it from mill back to the lathe, so that's quite convenient. I spent about 350 euros on this build, which is not too bad. I put some of the design files of this build on my website. Please see the description below for more information. I hope you liked this video. Thanks for watching.